Right now, while you are reading these lines, a decision is being hidden in the internal files of a laboratory in California that almost no one on Earth knows about. A machine the size of a small car, moving through the darkness between the stars, has been asked to do something it was never built to do. No probe has ever been asked this before, and no technical manual has ever described how to do it. This is not a new spacecraft. This is not a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the engineers now sending it commands were even born. It was only meant to operate for 4 years. To put that in perspective, the phone in your pocket has a longer battery life than its original mission plan. And this ancient little underpowered machine that was only supposed to fall silent in the early 1980s has now flown for 48 years and is still answering every time it is called. The engineers ordered it to become a different ship without using words like upgrade or adjustment. They used words like surgery, rewrite, and no way back. This is the story of Voyager 2, and this is the part the headlines do not tell you. What they asked this ship to do will keep you up at night, and what they just asked it this year is more shocking than anything before. Stay with me, because by the time this story ends, you will never look at Voyager the same way again. Subscribe right now if you want to hear more stories like this, because we are only just getting started. Late 1984. In a conference room at JPL, a group of engineers sat in front of a whiteboard. On it was a simple drawing. A dot for Earth, a long curve, a dot for Uranus, and somewhere on the curve a small dot representing the current position of Voyager 2. The mission on paper was simple. The 9-year-old ship would approach Uranus in January 1986, take pictures, collect measurements, then fly on toward Neptune. NASA had approved the extended plan 3 years earlier. The JPL team had had 3 years to prepare. It was supposed to be a successful minor encounter, a pretty postcard from a planet no one had ever visited, then the ship would fly away. What was really waiting for them was one of the most extraordinary technical challenges in the history of deep space. Voyager 2 had flown past Jupiter in 1979, sending back the first close-up images of the planet's surface the human eye had ever seen. It flew past Saturn and kept going, accelerating, using the gravitational pull of each planet like a slingshot. But every instrument on the ship, all 10 of them, had been designed for those 2 planets. Vidicon cameras to photograph Jupiter and Saturn, spectrometers to measure the atmospheres of Jupiter and Saturn, plasma detectors, cosmic ray counters, magnetometers, all of them. Not one instrument had been designed for Uranus, because Uranus had never been in the original plan. Then the JPL team started calculating the light. Jupiter is 5 astronomical units from the Sun. The light is 1/25th of the light on Earth. Enough for the camera to expose for a few seconds. Saturn is 9.5 astronomical units away. The light is 1/90th. Still enough. Uranus is nearly 20 astronomical units away. The light there is 1/400th of the light on Earth. To picture it, place a desk lamp 1 meter away from you. That is the light you get on Earth. Now imagine that same lamp placed 19 meters away, through the wall of your room, through the neighbor's house, and you still have to take a picture from behind it. That is Uranus. And at 64,000 kilometers per hour, the ship would have only a few hours before it flew past and lost Uranus forever. This was not a hard problem. It was an impossible problem. The light and speed problem we set out in the previous part needed a solution no one had ever thought of before. The JPL team could not make the camera expose faster, could not make the ship fly slower, but they could do something else. They would not keep the ship still while photographing. They would rotate the entire machine at exactly the speed the target drifted across the frame. The camera would be relatively still with respect to the target. The image would not blur. Imagine you are sitting in a car racing at extreme speed and want to photograph a bird flying the opposite direction. You cannot hold the camera fixed. The bird will only be a streak across the frame. The only way to get a sharp picture is for you, the photographer, to rotate yourself in the opposite direction at exactly the right speed to keep the bird centered in the frame. This technique has an official name, Image Motion Compensation, IMC, but it was not applied to a small camera. It was applied to the entire ship. The whole 722-kilogram machine, reprogrammed to pan slowly and under control while the camera was exposing. Here is the detail many people miss. Voyager 2 could already rotate about any of its axes at about 0.3 degrees per second, meaning more than 18 degrees per minute, by firing small thruster groups. This was the normal rotation rate for antenna pointing and routine orientation. But for Uranus, they did not need the ship to rotate faster. They needed it to rotate slower, and more precisely, only 2 degrees per minute, nearly 10 times slower than normal, but accurate enough that it could not be seen with the naked eye. Voyager 2 used 3 references to know which way it was pointing. A sun sensor mounted on the antenna, always seeking and locking onto sunlight. A star tracker at 90 degrees, locking onto a star of known brightness. A gyroscope at the center, tracking every change in direction when the other 2 sensors lost their lock. But when the camera was exposing Miranda for many seconds, the sun sensor could not be used, because if it turned toward the sun, the camera could not look at Miranda. The entire attitude system had to rely 100% on the gyroscope, at a distance of 3 billion kilometers, by radio. That was the first item. But it did not solve the next problem. The images could be sharp, but they still had to be sent back to Earth. And at 3 billion kilometers, there was not enough time to send the original images, unless they compressed the images before sending. But the FDS, Flight Data System, the computer that controlled the images on the ship, was full. There was no room to load a new image compression algorithm. No way to put more hardware on board. The machine had left 7 years earlier, and they could not simply overwrite the existing memory because every byte in it was being used to keep the ship flying. The detail many people also miss here is this. Voyager 2 had 2 FDS computers, primary and backup. The backup had never been used. It had sat idle for 7 continuous years, waiting for the day the primary computer failed so it could power up and continue the mission. The JPL team woke that computer up, not to replace the primary computer, but to give it a job it had never been designed to do: compress images. The algorithm they loaded was surprisingly simple. Instead of sending the full 8-bit value for every pixel, send only the full value of the first pixel in each row. For the remaining pixels, send only the difference from the previous pixel. Because neighboring pixels usually have similar colors, the differences are small and can be encoded in 3 bits instead of 8. The result? Images compressed to an average of 3 bits per pixel. A compression ratio of about 2.5 times, enough to send every image that needed to be sent in the Uranus flyby window. If the software was loaded wrong, if a single command line was mistyped during the uplink, the backup computer would fail. And they had no third computer to back up the backup computer. But image compression created a new problem. A problem the compression algorithm itself had created. If even a single bit in a row was corrupted during transmission, the entire row would be wrong, because every pixel depended on the one before it. If the first pixel was corrupted, every pixel after it calculated from it would be wrong too. A single bit error, possibly from electromagnetic noise as the signal traveled 3 billion kilometers, or from a cosmic ray hitting the receiving antenna at exactly the right moment, would destroy an entire row, sometimes the whole image. At Jupiter and Saturn, each pixel was sent individually, so a bit error only lost 1 pixel. Acceptable. At Uranus, with compression, a bit error meant losing an entire strip of data. Unacceptable. The solution to this problem had been built into Voyager 2 from launch, but no one had ever turned it on. It was called Reed-Solomon coding, a complex mathematical algorithm that allows detection and correction of bit errors after the signal has traveled an immense distance. If you send a message across 3 billion kilometers and 16 symbols in it are corrupted along the way, Reed-Solomon can still recover the message intact. Voyager 2 carried a hardware Reed-Solomon encoder from the day it launched in 1977, but the decoder on the Earth side, the computer that would receive the signal and decode it back into images with content, had not been built when the ship took off. JPL engineers spent years developing that decoder in parallel with the ship's flight. It was finished just in time, ready for the Uranus encounter in January 1986. This was the first time in deep space history that Reed-Solomon was used in practice. The bit error rate dropped 5,000 times compared with Jupiter and Saturn, while the ship's transmit power remained the same. The very encoder on the ship had waited 9 years to be used for the first time. That was the third item. There was still a fourth item on the ground, because the other half of every communication with Voyager 2 was not in space. It was on the ground, at the 3 deep space listening stations we talked about in the previous part. But at the distance of Uranus, the 3 stations were not used equally. Of the 3 stations, Canberra was chosen for Uranus, not because it was larger than the other 2, but because Uranus in the winter of 1985 and 1986 was at extreme southern latitudes in the sky. Only Canberra in Australia had the most favorable viewing angle. It could track Voyager 2 about 12 hours each day, compared with about 8 hours at Madrid and Goldstone. But even Canberra alone was not enough. So the DSN team did something no one had ever done for a planetary encounter before. They arrayed 3 antennas together. The first antenna was DSS-43, 70 meters in diameter, the main antenna of the Canberra station. The second antenna was DSS-45, 34 meters in diameter, built and completed in 1986, specifically to prepare for this Uranus encounter. The third antenna lay 200 miles northwest of Canberra. That was the Parkes Observatory, a 64-meter radio telescope, originally built for astronomy rather than deep space, operated by the Australian Science Organisation. They linked all 3 with a microwave cable across the Australian landscape. 3 antennas, 2 different stations, arrayed into one giant ear just to hear the whisper of Voyager 2. This was the first time in DSN history that antenna arraying was performed for a planetary encounter. Those were the 4 items, 4 major changes, 4 things that if each stood alone would already have been a major engineering achievement for any mission. But the 4 items were not carried out sequentially. They had to work at the same time, in the same moment. In the few short hours while Voyager 2 swept past Uranus and flew away forever, this team was no stranger to demanding extreme precision from the ship. 7 years before Uranus, when Voyager 2 flew past Jupiter, the only original target in the launch plan, it reached the Jupiter encounter point only 1.4 seconds late, and only 60 kilometers off the predicted path, at a distance of hundreds of millions of kilometers. If they could do that with a 2-year-old ship at Jupiter, they believed they could do something greater with a 9-year-old ship at Uranus. But 3 days before that moment, everything nearly collapsed. January 18th, 1986. 6 days before closest approach to Uranus. The JPL team was monitoring data when the first images began returning to Earth. The 4 items taught to the ship had been loaded months earlier. The camera had learned to rotate, the backup FDS had learned to compress, Reed-Solomon had been turned on, Canberra had been arrayed. Everything was ready. Everything except the images that arrived were unviewable, not soft, not blurred. Blur they understood, an IMC problem that could be fixed with a new command. This was something else. The images had long streak marks running horizontally across the frame, strange horizontal lines no camera could produce, random patches of missing data, as if a large portion of each image had been scrambled somewhere between Voyager 2 and the receiving antenna in Canberra. But noise does not work that way. Noise produces scattered errors. What they were seeing were structured errors, patterned, as if the ship itself was creating them. The entire team went silent, 3 billion kilometers, 6 days. The only chance humanity would have to see Uranus up close for decades, and the images arriving were streaks. People do not write much about the days that followed, even in the official mission records, perhaps because no one wanted to remember. The FDS team worked continuously with the very same backup computer they had taught to compress images a few months earlier, running diagnostics, trying configurations, comparing the corrupted data with reference data, asking the ship to send back different memory segments so they could read them directly. Each communication cycle took 5 hours 30 minutes, 2 hours 45 minutes for the command to reach the ship, 2 hours 45 minutes for the response to return. If they guessed wrong and sent a bad command, they would only know it after 5.5 hours. And finally they found it. A single memory element in the FDS had failed, a tiny piece of silicon small enough to be covered by the tip of a pencil. Not the whole thing, not catastrophic, just enough to corrupt one corner of the memory where the image compression algorithm was running. Every time the algorithm passed through that element, and it passed through many times for each image, the data was corrupted in an unpredictable way. That was why the errors were structured. That was why the streaks ran in the same direction. That was why electromagnetic noise could not explain what they were seeing. The element could not be replaced, could not be disabled by hardware. The ship was 3 billion kilometers away. No hand could touch that chip. But there was one thing they could do: rewrite the algorithm to avoid the failed memory element, break the image compression algorithm into smaller pieces, place those pieces into other memory locations they had carefully checked and knew were still good. Link the pieces back together so they functioned as a single whole. Never pass through the failed element at any step. This is what they did. Within 3 days, with a signal delay of 5 hours 30 minutes each cycle, that meant they only had 4 or 5 test cycles before time ran out. Each cycle had to be right the first time. January 21st, 1986, 3 days before closest approach to Uranus. Voyager 2 began sending back normal images, sharp, correctly compressed, error-corrected by Reed-Solomon, received by the 3 arrayed antennas at Canberra. The 9-year-old ship had become a different ship at the end of 1985, when the JPL team loaded the 4 items that taught the ship. And now, 3 days before the encounter of its life, it had also become the ship that had just been repaired, while still flying through the darkness. But none of that, not the crisis, not the 3-day miracle, not the 4 earlier items that taught the ship, prepared them for what was waiting on the other side. January 24th, 1986, 17 hours, 58 minutes, 24 seconds UTC. Voyager 2 reached closest approach to Uranus, 81,500 kilometers from the cloud tops. 1 hour before that moment, the ship had passed Miranda, the smallest of Uranus's 5 major moons, at a distance of only 29,000 kilometers. 18,000 miles. This was the closest encounter Voyager 2 had ever had with any body in its entire journey up to that point. Not Jupiter, not Saturn, not any moon in those 2 systems. Miranda, a moon only 470 kilometers in diameter. At the ship's speed, it remained in the camera frame for only a few minutes. If IMC had not worked, we would have had only a long, blurry streak across the frame. If image compression had not worked, we would have run out of memory before the images could be sent back to Earth. If Reed-Solomon had not worked, we would have received noise instead of data. If the 3 arrayed antennas at Canberra had not worked together, we would have heard nothing at all. 4 systems programmed by radio at a distance of 3 billion kilometers. 4 systems created or repaired after the ship had left Earth 7 years earlier. 4 systems that, until January 18th, had never worked correctly at the same time. All 4 worked. Miranda appeared on the screens at JPL with details so clear it silenced the geologists. Canyons as deep as 19 kilometers, 10 times deeper than the Grand Canyon. Ancient plains and young plains jostling together on the same moon, only 470 kilometers across, terrain that had been broken and reassembled. As if this moon had suffered a catastrophic collision in the past, the fragments gathering together and then flying apart again. And in the few short hours of the Uranus system flyby, Voyager 2 did not only photograph Miranda, it discovered 11 new moons and 2 new rings of the planet, more than the total of everything humanity had known about Uranus from 2 centuries of observation with ground-based telescopes. The first image of Miranda, and 11 images of new moons, and 2 rings. All of it the direct result of a 9-year-old ship that had learned how to rotate while photographing, how to compress while sending, how to self-correct errors while transmitting, and how to be heard by 3 antennas arrayed as one on the ground. Now jump ahead. Not 1 year later, not 10 years later, 37 years after that moment. After Uranus, Voyager 2 continued, as NASA's new plan had promised. It flew past Neptune in August 1989, completing the grand tour of the 4 giant planets. The machine built to fall silent in the early 1980s had now become the only machine in human history ever to approach both Uranus and Neptune. To this day, it is still the only one. No other ship has gone there since. No other ship is currently planned to go there in the near future. Voyager 2 is humanity's only record of the 2 farthest planets in the solar system. On January 1st, 1992, NASA officially named the new phase of the ship, Voyager Interstellar Mission. The Voyager Interstellar Mission. No more planets to fly past, no more grand tour to complete. Only one question remained. How far could the ship continue transmitting data when it was only Voyager and the space between the stars? On November 5th, 2018, after 41 years of continuous flight, Voyager 2 crossed the heliopause boundary, the outermost edge of the protective bubble that the solar wind creates around our entire system. The machine built to fly for 4 years had now become the second object in human history to leave the solar system and enter interstellar space. And it kept transmitting signals. By 2023, Voyager 2 was 45 years old, counting from its launch in 1977. The 9-year-old ship that stood before Uranus had become the 45-year-old ship flying between the stars. The same machine, the same 1970s hardware, the same Vidicon cameras that had long since stopped taking pictures. But one thing on the ship still would not stop. The RTGs, 3 radioisotope thermoelectric generators, devices that power the entire ship by converting heat from decaying plutonium into electricity, had operated without rest for 45 years. But plutonium does not burn forever. Each year, the RTGs lose about 4 watts. At launch in 1977, they supplied 470 watts to the entire system. By 2023, that number had fallen to about 260 watts. In those 45 years, the JPL team had done everything possible to preserve power for the science instruments, turning off non-essential subsystems wherever they could, optimizing operating procedures, trimming every watt that could be trimmed, making hard choices about which instruments should run and which should be paused. 45 years of trimming, 1 watt at a time. But by 2023, they stood at a boundary beyond which nothing more could be cut. Voyager 2 still had 5 science instruments running, collecting data from interstellar space that no other machine could collect, but power had reached the point where one of the 5 would soon have to be turned off, not because the instrument had failed, because the machine no longer had enough electricity to keep it running. This is the story that almost no one outside the JPL control room knows in detail. On Voyager 2, there is a small device called the voltage regulator. Its job is simple. If the voltage on the ship suddenly changes for any reason, the regulator activates a backup circuit that draws a small amount of power from the RTGs and stabilizes the voltage again. Think of it as an electrical life raft, held in reserve for emergencies throughout 45 years of flight. The JPL team looked again at that regulator in early 2023, and they realized something. In 45 years, Voyager 2's electrical system had been more stable than expected. There had never been a serious voltage event that required the backup circuit. The life raft had never been used. So what if they removed the life raft? The idea was simple. The power being held in reserve could be transferred to the science instruments, enough to keep the 5th instrument running for 3 more years, until 2026. But the cost was not light. If the raft was removed, any future voltage fluctuation, even small, could damage the instruments. No more protection system, no more safety net. The machine would run in what engineers call a naked condition. On a 45-year-old machine, at a distance of 20 billion kilometers from Earth, with a signal delay of 19 hours 30 minutes each way, If something went wrong in the night in Pasadena, the JPL team would only know about it after nearly 2 days. Suzanne Dodd, Voyager project manager at JPL, summarized it briefly. Voltage fluctuations are a risk to the instruments, but we determined that the risk is small and the reward is large, the ability to keep science instruments running longer. On April 26, 2023, JPL announced they had done it. The life raft had been removed. Voyager 2 began running naked. That is something you need to stop and think about. 45 years earlier, a team of engineers had taught the ship to become a different ship so it could see Uranus. 37 years after that, another team asked it to remove its protection system so it could keep looking. 2 teams, 37 years apart, asking the same question. How far can we ask this machine to go? Both times the answer was, farther than we thought, more than we dared hope. But that is not yet the point where the story stops. The man who signed the decision to retrain Voyager 2 in 1985 was named Richard Lacer, Voyager project manager at JPL from 1981. For his work on the Uranus encounter, NASA awarded him the Distinguished Service Medal, the highest medal the agency can give a civilian. He did not receive that medal for managing the project. He received it for teaching a 9-year-old ship to do something it was never built to do. The first principal scientist of Voyager was named Ed Stone. He had been with the project since 1972, 5 years before Voyager 2 launched. He oversaw the ship through Jupiter, Saturn, Uranus, Neptune, and both crossings of the heliopause. He also oversaw the decision to remove the life raft in 2023. He passed away in 2022, not long before the ship he had spent his life working on began running naked. The people who reprogrammed the backup computer to compress images for Uranus, in the engineering group under William McLaughlin, many had long since retired. McLaughlin himself passed away on May 31, 2025, less than a year before the day this video was posted. 3 names, 3 people. No one left at JPL to ask directly about what happened in that conference room at the end of 1984 when they drew the dot for Uranus on the whiteboard and began calculating the light. The ship is still out there. 143 astronomical units from Earth. 21 billion kilometers. Still running on 1970s hardware. Still running naked. Still sending signals back. Still answering after 19 hours 30 minutes every time it is called. 48 years after launch, the machine built to fly for 4 years is still transmitting data. On January 14, 2026, 10 days before the 40th anniversary of the Uranus encounter, JPL posted a short article on their history page. The article did not mention the 4 items that taught the ship, did not mention the 3 days that saved the FDS chip, did not mention that Miranda had been the closest encounter Voyager 2 ever had with anybody in its entire journey up to that point. The article simply said, 40 years ago we were there. No larger announcement, no grand commemorative event, no reporters invited, just 1 line posted at the right moment for those who knew to read it. But that is not yet the point where the story stops. 40 years after the first lesson, and 3 years after the ship discarded its protection system, NASA has just asked Voyager 2 to do one more thing. This one is larger than the 2 that came before, larger than anything they have ever asked. This is what I want you to hold on to when you leave this video. We usually talk about Voyager as a technical story, about the feats, about the numbers, but there is something the numbers cannot express, and the scientific papers do not write down. In the history of humanity, no machine has ever been asked to relearn as many times as Voyager 2. Not once, not twice. 4 times in 1 month in 1985, when the JPL team taught it how to rotate while photographing, how to compress while sending, how to self-correct errors while transmitting, and how to be heard by 3 antennas arrayed as 1 on the ground. Once in 2023, when it removed its protection system so it could keep looking, and once in this very year, 2026, the largest request of all. This machine was built to fly for 4 years. It has flown 48. It was built to see Jupiter and Saturn. It has seen 4 giant planets and a dozen moons no one had known. It was built to fall silent in the early 1980s. It is still talking to us in 2026. And every time it has had to learn something new, every time it has had to become a different ship from the one written in the original design, it has answered. Not perfectly, not easily, but it has answered. Remember the desk lamp 1 meter away versus the desk lamp 19 meters away through the wall in the neighbor's house that I told you about at the beginning of the video? That was the light at Uranus. That was the light equal to 1/400th of the light on Earth that the JPL team calculated in the conference room at the end of 1984. Where Voyager 2 is flying right now, 143 astronomical units from the Sun, the sunlight there is about 1/20,000th of the light on Earth. Put your desk lamp down. Now imagine that same lamp at the same distance as the place Voyager 2 is flying. You would not see it with the naked eye. Not dim, not weak, invisible. In a place that dark, this machine is still listening, still answering, still waiting for the next command from a planet it left long ago. and now they have just asked it to do one more thing, the largest request of all. The video in the upper right corner of the screen will tell you. If this kind of story is what you look for on this channel, subscribe and turn on notifications. Not because I need the views, but because there are stories that deserve to be told before the final signal arrives. Leave a comment with what surprised you most about Voyager 2 in this video. If you think someone else should hear this story, share it with them, because we have exactly one machine that has been taught to become a different ship more times than any machine humanity has ever built. And it is still answering.